In question number 6, infinite number of alternate charges Qn minus Q are arranged on a straight line with separation A. Find interaction energy of each charge with all charges. So suppose I am taking this as my charge, then the interaction energy of this minus charge can be written as U is equal to minus Q into electrostatic potential at the location of the charge. So that can be written as the potential due to this charge at this point will be KQ by A. Similarly, the potential due to the second charge at this point will be minus KQ by 2A. Similarly, we can write plus KQ by 3A minus KQ by 4A and so on. And we can see that the arrangement of charges on the left hand side and the right hand side of this charge minus Q is same. So we can multiply this equation by 2. On further solving this equation, we get this is equal to minus 2 times K Q square by A into 1 minus 1 by 2 plus 1 by 3 minus 1 by 4. So this series is the value of ln2. So we can write in this way minus Q square divided by 2 pi epsilon naught A into ln2 on substituting the value of K is equal to 1 upon 4 pi epsilon naught. So we can see that the correct answer for question number 6 is option 4. Let's move to question number 7. In question number 7, potential difference between center and surface of a sphere of radius r uniformly charged with volume charge density rho within it will be. So the potential difference delta V is equal to, we know that if the potential on the surface is V surface, then the potential at the center will be 3 by 2 times of V surface. So this can be written as 3 by 2 V surface minus V surface. So on solving, it comes out to be 1 by 2 of V surface, and V surface can be written as 1 upon 4 pi epsilon naught Q by R, and the value of Q in terms of rho can be written as rho into 4 by 3 pi R cube divided by R. So on further solving this, we will get rho R square divided by 6 epsilon naught. So option 1 is the correct answer. Let's move to question number 8. In question number 8, if electric potential of the inner metal sphere is 10 volts and that of the outer shell is 5 volt, then potential at the center is. We know that metal is an equipotential surface, so whatever is the potential at the surface, the same potential will be at the different points of the metal as well as at the center of the metal. So the correct answer for question number 8 is option 1. Let's move to question number 9. In question number 9, a rod of uniform charge density lambda and length L is placed vertically as shown. A point charge Q0 is placed at point O at a distance L from its one end. Potential energy of charge Q0 is equal to. So the potential energy of charge Q0 can be written as Q0 into electric potential at the location of the charge. So the electric potential at charge Q0 due to the uniformly charged rod. So in order to get this potential at this point, let I am considering an element at a distance x of length dx. So the value of this charge is dq is equal to lambda into dx. So the potential at this point O due to this considered element can be written as 1 divided by 4 pi epsilon naught into dq, that is lambda into dx, divided by x. And if I add the potential of all the elements at point O, then this would be integration x varies from L to 2L. So on solving, it comes out to be lambda into Q0 ln2 divided by 4 pi epsilon naught. So option 1 is the correct answer. Let's move to question number 10. In question number 10, consider the charge configuration and a Gaussian surface as shown in figure. If phi1, phi2 and phi3 are the net electric flux due to charges q1, q2 and q3 respectively from this Gaussian surface, then we have to find out the correct options, and it is given that q1, q2, q3 all are different and non-zero charges. So if I write the flux through this Gaussian surface is equal to charge enclosed by the surface, that is q1 minus q2 divided by epsilon naught. So this can be further written as q1 by epsilon naught plus minus q2 by epsilon naught. Now if I see the options, then phi1 represents the flux through this Gaussian surface due to charge q1, and charge q1 is positive, so the flux emanating from this Gaussian surface will be considered as positive, so the value of phi1 would be greater than 0. So phi1 is not less than 0. In option 2, phi3 is equal to 0. Yes, the charge q3 lies outside the Gaussian surface, so the flux through this Gaussian surface due to this charge will be 0. So option 2 is the correct answer. Similarly, for the charge minus q2, the flux would be negative, so option 3 is wrong, and the summation of phi1, phi2, phi3 is non-zero, so option 4 is also wrong. So the correct answer for question number 10 is option 2. Let's move to question number 11.